Hello and welcome to another video on applied electricity. Today I'm going to be looking at capacitors and capacitance. Here, when it comes to capacitors, a capacitor is simply a device that is used to store electrical charges. So in order to understand what a capacitor is, we have to start and understand what a charge is, right? So you know that if I have a charge, for example, a positive charge, right? There is going to be a magnetic and an electric field around such a charge, right? So any charge at all, whether negative or positive, you can find a electric field around the charge. That means there's an area around this charge whereby the charge can exert a force on another charge, or it can exert an influence on another charge. That is what we mean by what? Electric field strength. And within the electric field strength, depending on the kind of charge, you can have the charges, the electric flux, which are the lines of force within the electric field. You can have the electric flux diverging from what? From the charge, right? In the case of a positive charge, when it comes to a negative charge, they tend to converge. So you can see that they converge here. And this explains how attraction and reflection takes place when you have two charges, right? So let's say we have two unlike charges, positive and negative charge. You can see that because the positive charges, the electric flux diverge, and that of the negative, they converge. It means that the electric flux, the lines of force will start from the positive and ends at the negative charge. That will cause the attraction to take place. And when it comes to like charges, like positive two charges, right? You have two charges and they are positive. You see that they're going to repel you because all the electric flux for both of them, they are going to be in the same direction, right? I mean, they are all going to spread out or diverging. So if you bring them together, these lines will push apart, right? Because of the lines, they will charge push apart, and this is what referred as the repulsion. Now, we can talk about some characteristics regarding the lines of force or the electric flux, or we refer to them as electric flow lines. So you can see clearly that these lines, they don't form a closed path, right? They don't form a closed path or a closed loop. And these lines also are used to describe the magnetic field, right? We should describe the electric field, right? Use them to describe the electric field, and as well as to indicate also the strength of what the electric field, right? So, for example, if you have the electric field has been denser, right? It means you have a strong electric field, and then when it's weaker, you see a kind of very weak magnetic field lines, right? So these are some of the classes that you can think about, and there are quite a number of them. Now we move to the electric flux density. Electric flux density is the total electric flux per unit area, right? So if you have your charge, let's say positive charge, and you have this electric flux diverging from the positive charge, and they are passing through a surface, right, which is the area. So if you have the number of lines passing through this surface or area over the area, right, total number of lines passing through the area over the area, that will give us the electric flux density. And that will what? The total electric flux over area. And it happens to be the case that when it comes to the total electric flux, that's going to be the same as the charge. That's equal to the charge, which is equals to what? Charge, and that will be charge over area. And you can actually prove this by using Gauss's law, but this is beyond the scope of this topic, right? Now we move to electric field strength. When it comes to electric field strength, you think about it in terms of what? The force, right? And we know that if we have two charges, let's say charge 1 and charge 2, they're going to exert a force between these two charges, right? So that force, we can calculate the force, and we can do so by using what? By using Coulomb's law, right? And based on Coulomb's law, it says that the force is directly proportional to the product of the two charges and inversely proportional to the distance between the two charges. What this simply means is that if I have charge 1 and charge 2, the force is going to be directly proportional to the product of what charge 1 and 2 and inversely the distance between them like this. Then if you introduce an equal sign, so you have the constant k, and that constant k is going to be 1 over 4 pi epsilons, right? And the epsilons here represent absolute permittivity, right? Absolute permittivity. And absolute permittivity is what? Relative permittivity of free space times what? Relative permittivity, right? Of a material or medium. Right. Now we have our force. We can now try and get the electric field strength. What that means that when it comes to the electric field strength, we are trying to see how strong an electric field is. And what we tend to do is that we tend to look at this, right, in terms of what? A test charge, right? And we are going to make sure that the test charge is 1 Coulomb, right? So if I have any electric field and we think of what? Placing a 1 Coulomb within the magnetic field of the charge, right? Then you calculate that the force that is going to be exerted on that 1 Coulomb of charge, that gives us what? Electric field strength. So electric field strength is the force exerted on a positive test charge or the force exerted on 1 Coulomb of charge, right? So if you look at your force formula here, imagine charge 2 here is our test charge, which is 1 Coulomb. So if that would just be 1, you just get charge 1 over 4 pi epsilon times d squared and then the sin squared. So that will give us this one. So we have the electric field strength equals charge over 4 epsilon times the distance squared. And we can also think about the electric field strength this way too, right? We can think, if I have my force here, right? Imagine I want to make charge 2 to be 1 Coulomb. You see that I can just divide by what? Charge 2, right? And this will cancel. Charge 2 will end up and then I get the same thing. So I can just take the force here divided by what? Charge 2. That will give me the electric field strength. So that's why we have force over charge, the test charge. So that's another way you can define electric field strength, which is the force per charge, right? Force per charge. And once we have these parameters, right, these two important parameters, electric flux density and electric field strength, then we can look at it this way. If we were to take the electric flux density over the electric field strength, then you are dealing with free space, meaning you are in air. You get the permittivity of what? Free space. And it's a constant value, which is 8.854. That's it to power minus 12 farad per meter. Now, if you are in other media other than air, that means the electric flux density over the electric field strength will give you the absolute permittivity of the material. And absolute permittivity of any material is going to be permittivity of free space and relative permittivity of the material. So you can see this is exactly the same as the first one for free space. The difference is that when it comes to what? Air, the relative permittivity of air is 1. So hence we get this to be what? Permittivity of free space. So this is how you can talk about the charges that we have, and then based on these charges, we can try and get electric flux density and electric field strength, and then get the relationship between electric flux density and electric field strength that we have. Yeah. And if it's your first time of watching any video on this YouTube channel, make sure you subscribe and then like the video. So when we talk about capacitors, what are we talking about? Capacitor is an electron device that is used to store charges. So if you have a device at all and you can use it to store charges, we can call it a capacitor. Okay. So a capacitor consists of two parallel plates, right? Then you have a distance between the plates. Now imagine you have your capacitor, you connect it to a voltage source. What is going to happen is that as a result of this, there's going to be charges on the plates of the capacitor. Now we can try and relate the voltage that we supply and then the charges on the plates of the capacitor, right? Because once we have charges, that means we are going to have what? Electric flux. With electric flux, we can talk about electric flux density, then electric field strength, right? So we want to relate the strength of the electric field that is being experienced by the charges that we have here between the power plates that are on the power plates on the capacitor that we have here. Now, when it comes to voltage, we know voltage is the energy needed or work done required to move a charge from one point to another. So voltage can work done over charge. Then we can also get another work done, right? You can make work done over work done. We can charge times voltage. We can get another work done by moving a charge from the first plate to the second plate. So we get that work done by calculating the force times the distance, right? Between the plates. That will give us force times distance. We can equate the two work done. So we get this. Then that becomes, you divide both sides by charge, you get force over charge, and force over charge is electric field strength. Then you make electric field strength, so you get voltage over the distance between the plates. D. Now that we are able to determine the electric field strength, then we try and relate the charges that are going to be on the plate and the voltage, right? The applied voltage. If we increase the voltage, you realize that the number of charges is also going to increase as well, right? So increasing the voltage, increasing the number of charges on the plates, then we can write charges that are proportional to the voltage. Then we get the charge to bring an equal sign. Then the constant K as V, that constant is what we refer to as what K here is referred to as the capacitance. We make the capacitance the subject get charge over voltage. Once I have charge, I know that definitely I can get the electric flux density. So we make charge the subject from the electric flux density formula, which is charge over area. So this becomes electric flux density as area, and then over the voltage here. Voltage, we know electric field strength is voltage over distance between the plates. So we can replace the voltage with electric field times electric field strength times the distance between the plates. And that's going to give us electric flux density over electric field strength and times area over the distance between them. So electric flux density over electric field strength give us the absolute permittivity, right, of the material. So you can get this here. Then times area over D. So this becomes the formula for capacitance. And this is very important when you are trying to design a capacitor, right? That means that if you are designing a capacitor, that you have to place, or you can place a dielectric material between the power plates, right? That will give you the absolute permittivity of the material that you have. And depending on how much capacitance that you want to have, then you should probably have to start a dielectric with a very high watt with a very high permittivity, right? So here, this formula becomes very important when you are trying to design a capacitor. Then if you are dealing with air, meaning between your plates, you don't have any dielectric material, right? A dielectric material is just an insulating material placed between two paraplates of the capacitor, right? So if you don't have any material there, you get air. Only air is existing there. So capacitor becomes the permittivity of free space times area over the distance between the plates. And the permittivity of free space is a constant value, which is 8.854 times 10 power minus 3 farad per meter. Then once we have done this, you can see that based on the formula, we can try with different we can place different dielectric material between, and that will allow us to manufacture or design different kind of capacitor. So when it comes to how we classify capacitors, we can classify them based on three ways, right? We have three ways of classifying capacitance. One is according to the type of dielectric material between the plates of the capacitor. So if you use metal, ceramic, plastic, or paper, then we can refer to those capacitors as well. Metal capacitor, ceramic capacitor, plastic capacitor, or paper capacitors, right? Now, another way we tend to categorize capacitors is based on whether you can change the capacitance, right, of the capacitor. So we have fixed capacitance and variable capacitor. So that means that you can have a paper capacitor which is fixed, right? You can have a fixed paper capacitor or a variable paper capacitor, right? Then the last way we tend to classify capacitors can also be based on whether you can polarize, whether they can be polarized or not, right? So we have polarized capacitors and then non-polarized capacitors. Now that we have, we know how to design a capacitor, then we can look at another way in which we can try and increase the capacitance, right? Because by looking at this very formula, you can see that by increasing a capacitance that was area, if I increase the area, then I can increase the capacitance. If I decrease the distance between them, I would increase the capacitance as well. Or I place a dielectric material with a very high permittivity, I will also increase the capacitance that you can see. But there is another interesting way we can increase the capacitance. That method is what we refer to as interleaving, right? Interleaving is a way we can increase or enhance the capacitance by interleaving, in that case, meaning inserting parallel plates, right, into each other, right? So imagine, for example, you have two capacitors, right? And each capacitor consists of two parallel plates, right? If you were to insert them into each other, like you can see there, so I have 4 plates in this regard. And then once 4 plates, if they were individual, you get 2 capacitors, right? But since they are now interleaved, you can see I can get 3 capacitors because each 2 plates will give me a capacitor. So if they are interleaved, you get 1 here, another capacitor, and I'm getting to the capacitors. So you can see the number of plates that I have here, there are 4. And when they are interleaved, then I get to the capacitors. So imagine we had, right, 5 plates. How many capacitors are we going to get? Based on this, you see that we are going to get 4 capacitors. That means that we can relate the number of plates with the number of capacitors. If you have n number of plates, mean you can get n minus 1 capacitors. Then we come and modify the formula to reflect the number of plates with regards to the number of capacitors. So if I have n number of plates, then I'm going to have N-1 capacitor. So that's how this came about. Make sure you like the video and subscribe to this channel. Bye-bye.